When we think about death, right, we naturally picture an end, a failure, a total collapse. But what if I told you that on a microscopic level, death is actually one of the most sophisticated and absolutely essential biological tools your body has? It's the ultimate biological paradox. Let's completely deconstruct the paradigm of exactly how and, more importantly, why our cells die.
So, is cell death always a failure? We kind of have this tendency to assume that if a cell is dying, something has gone terribly, terribly wrong. But the reality? It's so much more fascinating than that. We really need to separate this into two completely different realities. On one hand, you have a catastrophic, totally unpredictable accident, and on the other, a perfectly executed, absolutely necessary biological sacrifice. And honestly, understanding the difference between these two is the absolute key to understanding human health itself.
Part 1. Necrosis, the chaotic accident. Let's look at the clinical definition of this totally unplanned event.
Necrosis is the direct result of irreversible injury. It's what happens when a cell is just completely overwhelmed by hostile agents, whether they're physical, chemical, or biological. And we can actually track this chaos right down to the cell's command center, the nucleus. Think of necrosis like a building collapsing unexpectedly. Step 1 is pycnosis. This is where the nucleus shrinks and hypercondenses. It's literally like a building compacting under its own weight. Then comes step 2, karyorrhexis, where that structure basically fragments and shatters to pieces. And finally, karyolysis. This is the complete dissolution of the chromatin, where the nucleus just turns to dust. It's messy, it's disorganized, and it is totally destructive.
And because it's such a chaotic accident, it actually manifests differently depending on where in the body this building collapses. For instance, we see coagulative necrosis in ischemic tissues, like during a heart attack. Then there's liquefactive necrosis, which usually hits the central nervous system. You've got caseous necrosis. That's the classic one you see in tuberculosis. And it doesn't stop there. We've got fibrinoid necrosis in ulcers, gangrenous necrosis from severe ischemia, enzymatic fat necrosis in the pancreas, and hemorrhagic necrosis. Every single one of these is just a different flavor of a biological disaster.
Which brings us to our second concept, apoptosis, the programmed sacrifice.
So if necrosis is the chaotic accident, apoptosis is its intentional, ultra-precise counterpart. It's programmed cell death. And the crazy part is, it happens without autolysis. That means the cell doesn't explode or leak its enzymes everywhere. Instead of a building collapsing, apoptosis is more like a highly controlled structural demolition. The cell shrinks on purpose, its chromatin condenses into these perfect little crescent moons, and all the cellular debris gets neatly packaged into clean envelopes called apoptotic bodies. Because everything is boxed up so perfectly, it completely avoids triggering any inflammation in the surrounding tissue. It's just a flawless, silent exit. But how does the cell actually know it's time for this demolition? Well, it relies on two main technical pathways. First, you have the intrinsic pathway. Think of this as the internal alarm bell. If there's DNA damage or a lack of oxygen, mitochondrial proteins like cytochrome C, which are regulated by factors like BCL2 and P53, trigger the sequence from the inside out. Then, on the flip side, you have the extrinsic pathway. This is an external biological order. Receptor ligands, like Fas or tumor necrosis factor, effectively act like a message from the outside saying, hey, your time's up, initiate self-destruct.
And that brings us to the ultimate showdown, the duel, necrosis versus apoptosis.
To really wrap our heads around these processes, we've got to put them head-to-head and look at the trade-offs. By its very nature, necrosis is strictly accidental, right? While apoptosis is meticulously programmed. When we look at the causes, necrosis is always driven by irreversible lesions or trauma. Apoptosis, well, it can be pathological, but it's also physiological. It actually has a biological purpose for happening. But the ultimate biological trade-off? That's inflammation. Necrosis always leaves collateral damage, sparking this chaotic inflammation. Apoptosis, on the other hand, operates in total, perfectly clean silence.
Zooming out from the microscopic view, let's look at the clinical impact. How does this play out in the real world?
So, why does differentiating these two mechanisms even matter for medical research? Honestly, it matters because of what comes after the death. When a cell undergoes necrosis, the aftermath is harsh. It leaves permanent scars through fibrosis, or it leads to dystrophic calcification, which is basically when abnormal calcium salts deposit right into the dead tissue. It leaves a permanent mark of damage. But apoptosis? Apoptosis actively shapes human life. It's responsible for embryogenesis. It literally sculpts our fingers in the womb by cleanly removing the cells between them. It drives hormonal involution and healthy cell renewal.
Simply put, necrosis leaves a scar, but apoptosis paves the way for the future.
If there is literally only one thing you take away from this explainer, let it be this verdict. Cell death is not just an end, it is a biological choice between a chaotic collapse and an orchestrated vital renewal. It's the ultimate balancing act that keeps us functioning every single day.
I want to leave you with one final kind of provocative thought. Which mechanism do you think is ultimately more critical for human survival? Is it our body's ability to survive and isolate the chaotic cellular accidents of necrosis? Or is it our ability to flawlessly execute the silent cellular sacrifices of apoptosis? I'd love to hear your arguments on this. Drop your thoughts in the comments, debate it, and keep trying to understand the incredible machine that's operating inside of you right at this very second.